Hello everyone. We are starting a free open lecture in our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions and receive answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. Today we will study the Fibonacci heap. It is an improvement over the binomial heap, but not quite. Later, we will discuss why. That is, let's remember what we are essentially aiming for in terms of complexity. If we initially started with a binary heap first, the operations it could perform included such tasks as adding an element in logarithmically efficient time. It could also delete the minimum. The same goes for the algorithm. It could also obtain the minimum in constant time. Merge operations were performed in a minimum of n on m. This process can be executed using a specific algorithm. The algorithm ensures that n on m is achieved efficiently. The merge operation is crucial in various computational tasks, ensuring optimal performance and accuracy. So n and m are the sizes of the two heaps that we are merging. We are merging the smaller heap into the larger one. Therefore, here we go through the entire smaller heap for element removal. This is insertion and deletion. Well, decrease key was also an operation. The decrease key operation was performed. Algorithmic complexity of t. We just needed to move upward. So, moving on. The binomial heap. Basically, it was exactly the same, except that the merge operation was performed in logarithmic time. And now we essentially want to examine in detail the Fibonacci heap, which can do what, in essence, it can do this basically. In our case, pop will take logarithmic time, insertion of elements will take constant time, finding the minimum will also take constant time, merge will take constant time, and deletion of a key and decrease key will also take constant time. This is the data structure we want to implement. Well, if there were a 1 here, then this wouldn't be the case, because there is a theorem that states we can only sort in n log n time. And if there were a 1 here, we could sort in linear time. Therefore, if there are any data structures that allow adding elements, deleting them, and also retrieving the minimum or maximum, that is, these are data structures that maintain order, and at least one of their operations will be performed in logarithmic time in the best case. It will not be the case that a third of the operation will be performed in constant time or less than logarithmic time, because that is impossible. Yes, hello, volume sorting.
Want to become a great programmer? Subscribe to our Telegram channel.
What do we need to study for the Fibonacci heap? We need to study some improvements to binomial trees that will be used in this data structure in order to thoroughly and effectively understand it. Well, let's recall what a binomial tree is. It is a tree that has a rank. I will write the ranks here, not the values. A tree of rank 0 simply looks like one node. A tree of rank 1 looks like. A node is attached to another node of rank 0. A tree of rank 2 looks like a tree of rank 0. With the first node, the second node is a tree of rank 1. Now let's draw a tree of rank 3, which means node 0 is a node that is a tree of rank 1, and there is also another node here. That is a tree of rank 0. And here, accordingly, with ranks 1 and 0. In principle, we have essentially studied this, but what is the downside of this tree? This tree is too strict, meaning that these children are very rigidly positioned within it. Each must be in its very specific place. This does not allow us to have some flexibility, which is why there is a logarithm here. In many operations, it remains. To get rid of this algorithm, we need a slightly different tree. Here we need to establish, well, more precisely, some properties. What property? If we have a binomial tree of rank k, then it will have 5 children of certain ranks, which means that each of these children will have specific ranks that are determined by the structure of the binomial tree. That is, here we have rank 0, here rank 1, here rank 2, and so on. Here we must have a child of rank k and minus 1. This is the strictness. In order to make it less strict, we can also use a binomial tree, but what kind of children will be here? here we must have a tree of rank greater than and equal to 0. That is, there can be a tree of rank 1, a tree of rank 2, 3, and so on. There can even be a tree of rank plus 10. It's all quite fine. Here we will have a tree whose hierarchical rank is greater than or equal to 1. Here, in this example, the rank is greater than or equal to 2. And in the end, we will ultimately have a child node whose rank is definitely greater than or equal to k1, certainly. And with such trees, we can indeed perform some other operations more lazily. That is, if in a binomial tree we must place a tree here that has a rank of only 0 and nothing else, then here we can already place a tree that has a rank of 0 or higher, and this gives us more freedom of action. This is the first point. Secondly, we also have trees with stars appearing here. What is a tree with a star? In fact, a tree with a star is needed only for one operation, to reduce the key. If we do not, in general, generally speaking, carry out this operation, then we will not need a tree with a star. What is a tree with a star? It is a rank k tree with a star. This tree is still of rank k, having essentially the same properties as a regular rank k tree, but there is one nuance. It has not k children, but k1 children. That is, our last child here will be a tree with a rank greater than or equal to k2, if we had it here. So, a rank k tree with a star will have k1 children. This is essentially the difference between a rank k tree and a rank k tree with a star, which still has k1 children, while here it has k. But it still remains a rank k tree because, well, it's as if this is essentially the same as a rank k1 tree. If we look at it, k1, and here we have everything matching. A rank k1 tree has k1 children. Here, everything increases in such a way that the last child must have a rank greater than or equal to k2. So what is the difference between these two trees? The difference is that I can freely attach another tree with a rank greater than k1 to this tree, and it will essentially become a tree of rank k without a star, basically. And if I somehow hang some child onto this tree, it will slightly change its rank and become a rank k tree. The rank will slightly increase. Here, our rank will not change, and this will be needed for the paint of the star, which is an essential part of the process. So let's consider what the maximum height of such a tree will be, taking into account various factors. First, let's examine what types of trees can exist, considering different species and their characteristics. Well, for example, a rank 0 tree. A rank 0 tree, by the way, cannot have a star. Why can't it have a star? Because a rank 0 tree is ordinary. It has 0 children. It has no children. Then by def, a rank 0 tree with a star must have one less child than it has without a star. Therefore, such a tree must have -1 child. This violates all common sense, so a rank 0 tree cannot have a star. Now let's talk about the rank 1 tree. What could it look like? We could have a rank 0 tree hanging here. We could have a rank 1 tree hanging here. We could have a rank 2 tree hanging here, and generally anything greater than or equal to 0. That is, if in a polynomial tree we must have 0 here, then in our so-called Fibonacci tree, there can be anything greater than or equal to 0. Additionally, there can be 1 hanging here. This also works because rank 1 is greater than or equal to 0. So let's say 1 with a star. A tree of rank 1 with a star, but here it's simple. It simply won't have any children because, again, by definition, if a tree is of rank 1, it must have one child of some kind. If it has a star, then we remove that one child. This is roughly the same as a tree of rank 0. A tree of rank 2, what might it look like? It must have 2 children, so what kind of children will they be? Here we will have anything that is greater than or equal to 0. This means we can have 0 here, we can comfortably have 2 with a star here, or we can have 1 with a star. Here we should have everything that is greater than or equal to 1. That is, for example, 1 with a star can also hang here. There might be a double or something. There could be 2 with a star, 3 with a star, and so on. Well, let's say I'm here. Well, some kind of 2. That is, there can only be 0 here, but it cannot be present. And for 2, there must definitely be 2 children. And what about these 2 children? Well, 0, for example. And here I will take 1 with a star. Or you can simply have a 1 here. One child is mandatory, and its rank is greater than 0 or equal to 0. Let's say 1 with a star. All of this is actually correct Fibonacci trees, meaning they are valid. There are no violations here. For rank 2, it means 2 children, and the unit is greater than or equal to 0, but only greater than or equal to 1. Let's try to draw 2 with a star. 2 with a star means that such a tree will have only one son. There is no Rob because we have a star, but one son can be like 0, it can be 1 1 with a star. 2, I don't know, maybe 10 of some kind. But all of this fits here. Well, there are 3 3 with a star, and so on, it will work. So in fact, we can easily build a Fibonacci tree with bamboo. For example, here we have 1. Here we have another one, because it fits the definition. Here it should have 1 more child. Another one, like this. And here we have, for example, a 1, and at the end there is either a 1 with a star or a 0. And this also fits the definition of a Fibonacci tree, because the frame of the child must be greater than or equal to 0 if there are no children at 0 already. Therefore, this is all either bamboo, and it can be a Fibonacci tree. Moreover, such a structure can result from a certain sequence of operations.
Want to become a great programmer? Subscribe to our Telegram channel.